Rates of change. Let's start by considering a rate of change we are all familiar with. We know that speed is equal to distance divided by time. So speed is the rate of change of distance with respect to time. It is a rate measuring the distance travelled in a certain amount of time. If the speed is constant, then we get a straight line on a distance-time graph. So here's a straight line on a distance-time graph, and indeed the gradient of that line would give us the speed. So the speed can be determined by measuring the gradient of the line. We can do that in a familiar way using rise over run. And the question is, how can we do this if the distance-time graph is a curve instead of a line? So suppose we had something like this, and we can see now that it's a curve. One approach is to think of average speed by considering a chord and calculating its gradient. So the average speed would be given by this line, and we could work out the gradient of that line. But what if we want the speed at a particular time and not just the average speed? We need to consider the gradient of a tangent to the curve. So in other words, a tangent line such as this, which would give us the speed at this point, or like this, which would give us the speed at this point. Clearly, the speed is changing. That's why we have a curve. If we can calculate the gradient of the tangent at any point, we will get what's known as the instantaneous rate of change. That's the rate of change at that particular time. There is a problem, of course, that we only know one point on this tangent. So if we're considering this tangent here, the only point we know is that one there. And we need 2 points in order to find a gradient, otherwise we can't get a rise over run. We're going to deal with that problem shortly. In fact, that problem is the whole heart of differential calculus.